Hey, good morning, everyone. I'm Petros Samartzis. I'm gonna focus a little bit more on chemicals. So, this is an overview of the talk. We'll talk a little bit about principles, hazards, the categories of hazardous chemicals, labeling, and then hygiene rules, protection, safety rules, a bit more on personal protective equipment, PPE. You'll hear that a lot in safety talks. How to dispose of chemicals, and then a few references. Please note that this is not a cover-it-all talk. It's impossible to give a lecture on safety and last only on chemicals and last only an hour. This is a sort of a teaser. So in each lab, you'll use different chemicals, different techniques, different methods, different tools. You should be curious to look a bit more into your own safety. And you must, if you want to stay alive in the lab and not acquire cancer after a few years, you should go through this presentation, use it as a source of information and as a beginning to search even more. So, there are two things. When you go in the lab and use chemicals, you should be first aware of the hazards, meaning what can the chemical do to you, what can happen to you, and then also be prepared for the possibility of an accident. Nobody wants to be in an accident. Nobody intentionally causes an accident, at least from the people I know. But accidents happen, and we have to be prepared for them. A few definitions. When is a substance hazardous? Well, first, if it poses a physical risk, and second, if it causes either an acute or a chronic health effect. So note that if statistics are not a big part of this, but they increasingly get into play. What is a physical risk? If something is flammable, it's a physical risk. If it's something compressed, you have a compressed gas, you have a physical risk. If you handle an explosive, the explosive is a physical risk. If something is easily catching fire, like phosphorus, it's called pyrophoric, and it's also a risk. If something is unstable, also a risk. I'm not sure I need to explain, but I will do it anyway, what acute and chronic is. First, what toxicity is. It's the degree to which a substance can damage an organism. And when we refer to an organism, it can be a cell or an organ or a whole body, an animal or a person. And it can be either acute, so you come in touch with the substance, you eat the substance, you breathe the substance, and then something happens to you, bad, usually. And it can be also chronic. You handle the substance today and you get cancer in 20 years. By the way, I wanted to mention, if you want to interrupt me, if you have a question, please do so. Open your mic and interrupt. Okay. Now, the effects of the chemicals in terms of safety depends on keeping up with good laboratory practices. If you don't follow them, the effects won't be very good. The substance's own properties, physical, chemical, biological. How much you use, it's different to use a nanogram of mercury, different to use a ton of mercury. How you handle, store, transport, use chemicals. If you handle acids with bare hands and you dip your hand in an acid, you do it at your own risk. The duration of contact, it's one thing to use a substance for a second, just move it from one container to another, and a different thing to use huge quantities of that substance every day, 365 days per year. How many people are involved? I mean, it can be only you. It can be 5 other people that are doing the work together. And then how you dispose of chemicals. So how do we get in touch with chemicals? We can breathe them, we can eat them, get them in our mouth, in our intestinal tract, or they can come in contact with skin or our eyes. Special attention in inhalation or skin and eye contact. Both the lungs and the skin have high surfaces, which means that they are potentially, even a small quantity of the chemical can spread and stay there for a long amount of time. Okay, a few, let's say I would call them buzzwords, a few terms that you will see around, like TLV or LC50, LD50. It's basically, you have them here as a reference. TLV is basically how much concentration of a material for a defined period of time is allowed, is sort of safe. I would go below that amount. LC50 is how much concentration of a chemical keeps 50% of a sample population, usually mice. LD50 is the same thing, but now they have to swallow it. The first one was breathing, and so forth. Now, categories of toxic substances, of chemicals, sorry. We have toxic chemicals. We have lung, neuro, hemo, kidney toxins, carcinogens, teratogens, allergens, corrosive or caustic chemicals such as acids, bases, desiccants, oxidizing agents. I'm passing these fast through. I'm not naming all these chemicals because some of you might not be using them anyway, and you can always come back to the slides and use them as a reference, so it doesn't make any sense to just read names. Explosives, and you have a long list here of things that you might not at first sight think as explosives, such as, I don't know, ethers, dry ice, CO2. It's not explosive, but it is. Chemicals that react violently with water, alkali metals, calcium carbide, metal halides, phosphorus pentoxide. And you have pyrophoric, substances that ignite spontaneously, that catch fire fast. Light sensitive, once they see light, they decompose. Cryophoric, this is a fancy name for liquid nitrogen and liquid helium and all other substances that you use in baths when you need to reduce the temperature, such as dry ice and isopropyl ether. And you have other dangerous chemicals such as acetylene, ammonia, CO, chlorine, and so forth. One moment. So that's all compressed gases. Moving on to labeling. These are the categories of chemicals. Why do we go through them? Not to know that we separate chemicals into categories, but because groups of chemicals, a category of chemicals has most of the times common handling, some basic rules that you should follow. If you have caustic substances, do that. If you have carcinogens, do that. And we need to know which group each substance falls in. Note that a single substance might fall in different categories. It might be a gas that is carcinogenic, catches easily fire, so it's flammable, and so forth. Now, labeling. In the bottles that you buy, you will see usually this called NFPA diamond, which is an easy way to show information about the danger of chemicals. The red, it has 4 areas, red, yellow, blue, and white. The red is about the flammability. The yellow is about chemical reactivity. Blue is about health, and white is special information. You should know that. You should keep that in mind. Because even if you don't read the MSDS, from that diamond, you have basic information about the chemical. And now, 0 in that diamond means that it is relatively safe. 4 is most dangerous. So 0 in fire hazard means it doesn't catch fire. 4, it ignites very easily. Health hazard, 0 means basically water. 4, it's deadly. And in the white area, you will usually have a name, acid, alkaline, corrosive, oxidizer, and so forth. That gives you a special warning about the chemical. And you see here 2 bottles that have these diamonds. Another system that is usually used is the globally harmonized system, or the pictogram system. That's why it has these little images. You have these rhombs. It's red rhomb, and inside you have white background and black picture. And the pictures are, well, intended to be self-explanatory. The exploding bomb signifies an explosive reactivity hazard. A falling cylinder means, oh, a gas. This body with this star in the chest means a health hazard. Exclamation mark, it means danger, somewhat less than the usual. These things dropping and causing issues that look like acids means corrosion. The flame, of course, it's fire, and so forth. Here there are 2 European regulations that you can look up and have basically lists of chemicals and how you put them in different groups in terms of safety and what pictograms they should have. Now, a more detailed look on MSDS. MSDS is the first thing that you look for when you buy a chemical. Before you buy the chemical, you check out its MSDS. So you design an experiment, you decide that, okay, I need that chemical, and you go buy it. Before you buy the chemical, you download from the company. Every company that produces chemicals must provide you with material safety data sheets, and it's free. You don't have to pay for it. And you usually download it from the site of the company. Here you see a list of the sections that material safety data sheet can have. I won't go through reading this list because we'll see them in detail in a sec. It's important that not only that you download it, that you keep the MSDS in the lab for every chemical that you use. And this is a requirement that the MSDS should be in the lab. Now, what does a safety data sheet contain? It contains the name of the product and the address, the contact for the supplier. If you have a question, you can ask the supplier. That's why this is there. Composition. Why is the composition here? Because some chemicals have leftovers from the synthesis that you need to know. Hazards, an important part. What it can do to you. And it has routes of entry, the effects of acute exposure, and so forth. This is an example by the way, for methanol. First aid measures, what you do in case of an accident. These, I warned you, are kind of general. You will see the same instructions for HCl and the same instructions for methanol. Skin contact, wash. Eye contact, remove contact lenses, or usually do not wear contact lenses, wash for 20 minutes, and so forth. They are important. If there are special instructions, you will see them here. Firefighting, it'll give you information like flash points and explosion limits, not for all chemicals, but it basically tells you, and notice here where it says extinguishing media, says dry chemical CO2 water spray. Why does it say that? Not all fire extinguishers are born equal. As far as I know, in our labs, we have CO2 fire extinguishers and dry chemical, dry dust extinguishers that are good, that are proper for most of the chemicals or all the chemicals that we use, including in electrical fires. We don't have water extinguishers, and we should not, because water might fuel some fires, like electrical fires. So we don't want them there. But what I want to say here is be careful that the extinguisher you have in the lab is appropriate for the chemicals that you have in the lab. Okay, next. 6. What happens if you accidentally release the chemical? Nobody's hurt, but it's a spill. What personal protection to wear, what you do for environment, how you pick it up. Handling and storage, how you move around the chemical, how you transport it from one container to the next, and how to store it, what it is compatible with, what it is not compatible with. Exposure controls, usually this tells you what kind of gloves to use, what masks to use, footwear, if any special footwear is needed, and so forth. 9 is physical and chemical properties. It has things like freezing point, like boiling point, sometimes ignition temperature, vapor pressure, and sometimes you will see Na not available. It is very common. So sometimes you have to go beyond the material safety datasheet to see, for example, if a chemical has sufficient vapor pressure. It's dangerous because it has vapors. Stability and reactivity, how stable it is, what chemicals it cannot tolerate, what it will react immediately with. Why is it there? Because you don't want to store, for example, acids with bases right next to each other. They will react. Toxicological information, now you see these LD50s and LC50s and the other things we started with. Eco information, what it can do to the environment. And that, what it can do to the environment is very much connected with, the next, disposal considerations. So if something is bad for the environment, you don't put it in the sink. Disposal tells you how to dispose of it, and transport has information about how to move it around. Most of the time, this is about companies that move huge quantities, but if you go through these classes, you'll see that sometimes it applies to us as well. Regulatory information, all these are sort of bureaucratic, but it's good to dig in sometime, and any other information that needs to be provided. So that's all about material safety datasheet. Now we'll go through a series of tables. Any questions so far? I don't hear anything. Okay. Through a series of tables that give you a sort of a taste of what is not compatible with what to do in certain situations, and so forth. So here is a chemical compatibility table that tells you on the, let's say, y-axis, it has a list of chemicals, and on the x-axis, it has the same list of chemicals, and the x is where there is incompatibility, when one chemical doesn't like another. So organic acids and inorganic acids do not go with each other. Maybe I should change. I can't do it. Should change my pointer to a laser pointer. Okay. I hope you can see my pointer. So for another, amines and acids, organic or inorganic, do not go together, and so forth. And these, whether is void, there is no X. For example, 13 esters are compatible with 8 ketones. I cannot move there. Another table of compatibility. This is a little bit more colorful. Green, okay to store together. Orange, light, and more dark, segregate. I mean, you can put them together, but better have a distance, and it tells you how much distance, 3 meters in some cases, more in others. And you see this red, isolate. Don't put it with other chemicals. Another sort, if you look up the web, you will find a lot of these tables. So if you have a chemical and you're wondering, can I use it with another chemical? Look it up. It will be, some information will be in MSDS, but if MSDS doesn't say anything and you have a suspicion that something is not, you have to be certain, just go online and look it up. This is about plastics. So basically, can I put a chemical in a container made of acrylic, of acetal, of CAB, the PVC, and so forth? And it tells you A is great, do it. Another letter, don't do it, and so forth. There is a range of do's and don'ts. Another source of information from Cole Palmer. Chemical compatibility. You have a chemical, and then you want to see if it's compatible with another. You put it here. Here is an example of aluminum and acetaldehyde. Compatibility, be good. What does it mean? It means that acetaldehyde will eat up aluminum, but it will do it slowly. So if you leave acetaldehyde in an aluminum container for years, eventually you will have a leak, but it is okay for a few hours or weeks or a month. Now, safety rules. I see that this is a long list, but let's go through it. When you are thinking about using an experiment, chemical in an experiment, you have to know where it is listed in, which hazard category you have there, what PPEs you will need, where you're going to work, and what space you need. For example, if it's a flammable, you don't want to put it next to a fire source. If you will need special equipment, does it need to be handled in a fume hood? Does it need a glove box, special environment, inert gas maybe? Need for special storage, separate from other chemicals? Maybe you need to get a permission of license. This is a little bit far-fetched, but some materials need licenses. How to clean up and how to dump the waste. You did your experiment, you have waste, what to do with them. And then, of course, this is the risk assessment when you go through all the stages of your experiment and you think, what do I do if something goes wrong here? What do I do if something goes wrong there? And so forth. And you have ways to react, to respond when you need them. If you wait to do that in an experiment, most of the times you end up in a disaster. We are lucky so far that these disasters have not proven to be with serious injuries or deadly. So, use of chemicals. Anastasia said it already, no eating, drinking, and smoking in the lab. Actually, smoking is forbidden almost everywhere in the building. Second, lab needs to be clean and neat. You need to be able to find what you need fast. You don't want to search for a screwdriver through all the drawers in the lab or for a beaker that, I remember I put it somewhere. Then you need to know the location, type, and use of appropriate safety equipment. You need to know where your fire extinguisher is. You need to know how to use a hood, how to use a glove box, how to use shields, gloves, and so forth. Obviously, you avoid getting exposed to fumes, gases, or aerosols. If you have such a thing, use a hood. Wear comfortable clothes. When we say comfortable, we don't mean too loose or too tight, just to be able to do the job. You don't want to have a tight outfit that stops you from moving your hands. When you wash hands with soap and water, not with organic solvents. Why? Because the solvents penetrate the skin and it will get any chemical on your hands even deeper. If there is an emergency, you warn everybody, and this is politely said. You should, if you need help, you should yell help. Not all the lab should hear you, all the floor should hear you. This is not the time to be shy. And always you act in accordance with general and personal laboratory safety rules. Some laboratories have special rules because they have special chemicals. You need to know them. And always you have to exercise common sense. So if you want to pour acid out of a container and you don't have a pour, it's not a good idea to use your mouth. It's common sense. Disposal. Do not dispose, well, not everything can be disposed in the sink, down the drain. Not only because you can have a toxic substance that you spread around in the environment and you can kill people and animals, but because you can also destroy the draining system and cause trouble to the technical services and to colleagues around. You use, especially for toxic chemicals, special containers for toxics. Sharps, you don't throw away in the normal trash can. You have special containers for those, and that includes needles and broken glass. And there have been cases here at Forth that the cleaning personnel finds needles or broken glass in the trash bins. Don't do that, period. We'll come back to disposal a little bit later. And storage. Now, all chemicals should be put in suitable, tightly closed, not for some very high vapor pressure chemicals. You need to leave the lid a little bit open for the vapor to go out. Definitely labeled and properly stored containers. When you put a chemical in a container, label it, because you know what it is, but the other people don't. Try to keep records of your chemicals, because we tend to order things and reorder the same things because we forgot where we put the first ones. Label also drawers, closets, shelves. When you use a chemical, put it back in its place. Don't change its place, because the next guy that will use the chemical will not find it and will order it, and then we come up with a huge quantity of chemicals that we have to throw away, and we pay to throw away chemicals, especially toxic ones. And the last one is related. If you need a chemical and you don't have it, before you buy a quantity, ask around, do you have this? Because usually if you need a small quantity, chances are that somebody else already has bought it and he or she can give you that quantity. How do you handle chemicals? You see the picture here. You use both hands. You don't hold it from the lid. The lids are very tricky things. They fall. They are open. If they're loose, the container will fall. And if it's I don't know, ethanol, no big deal. You have to clean up. But if it's an acid, you're in trouble. So put your hand under the bottle as well as on top of it, and don't hold it from the lid. You need then this is for taking, you know, from the cupboard and moving it 1, 2, maybe 3 meters away. If you need to go to the storage room and get a chemical and move it to your lab, and it's, I don't know, 10, 20, 30, 50, 100 meters away, or on the next floor, use these buckets. We have rubber buckets around the labs that are for transporting chemicals. You put the container in there and you take it with you. Why is it there? Because if you slip on the floor and fall down, the rubber will prevent the container from breaking. That's the idea. You don't have a bucket, use a cardboard, a box. Cardboard box, put the chemical in there, or maybe 2, just to be safer, and take it with you. Special notice for chemicals. You need good ventilation, for flammables, sorry. Don't use ignition sources next to the chemical. And there are a list that includes electrical equipment, hot surfaces, smoking materials. If possible, do not use flammables. And if you need an open flame, follow that list. Warn everybody, hey, I'm going to use a burner, remove the flammables around it, tie your hair back. You don't want to burn your hair. Never leave the flame on and unattended. At all times, keep full control and be extra careful. And notice here, chemicals are sometimes flammable chemicals are stored in fridges that are not designed for flammable chemicals. And flammable chemical or explosive proof, let's say, fridges are extremely expensive, and PIs are usually reluctant to get them and put them in a lab. Hopefully that will sometime change. That has to do with chemical storage. Put them in suitable containers. If you have a spill, you should keep it contained and, of course, prevent it from spreading. And you need to know where your fire extinguisher is when you use flammable chemicals, and try to keep the quantities low. No need to have a barrel of ethanol in the lab, 50 liters, so that you don't, go to a warehouse and pick it up from there. Even in a warehouse, chemicals should be kept a little bit away from each other, not all flammables together. If one catches fire, we're doomed. Toxic chemicals. Everybody that uses toxic chemicals, first of all, they should know what kind of toxicity you have, how you can get exposed to it. Can you breathe it? Of course, you cannot eat it. I cannot imagine of any case where you digest a chemical. And that is precisely why you don't need food in the lab, because a chemical might accidentally get on the food and then bye-bye. And then what category it falls in. There is a note here in red that sometimes the reaction can produce a chemical that is more dangerous than the initial the reactants. You see here in the reaction with ammonia, with sodium hypochlorite that produces hydrazine. A note about gases. We use them, especially in laser labs. I'm sure they're used in Imbb as well. You need each cylinder to put it on a wall. And I'm not referring to this plywood wall. I mean brick walls. And you see the proper way to do it here in the top right, I should say. You don't do this thing, the top left. These are a bunch of cylinders just left there. If there is an earthquake, these can turn into torpedoes. And in the bottom, you have a green tick and a yellow face. I have to comment that these refer to how these cylinders are attached to the wall and not how the let's say the substance is moved. Why? Because if you look on the right, they have regulators, and that's the proper way to go. And on the left, you just have a tube, and that's it. This is not the proper way to go. Always with a cylinder, you use a regulator, and an appropriate regulator to go with it, because not all regulators are born equal. There are regulators for corrosive gases, there are regulators for noble gases, and there are other kinds of regulators special for special gases. Okay. Liquid nitrogen, liquid helium. Again, common sense kicks in. You use proper transfer equipment. You don't put it in a glass container and just move it along and say, oh, it'll be all right. Nope, you have to have a dewar. You avoid overfilling, spilling, splashing. And I should also add playing with liquid nitrogen. This is not the time to put your finger in to show that you're brave. You might end up without a finger. You don't touch cold surfaces, the tubes that transfer liquid nitrogen from the large container we have outside into the dewar. Especially don't play that game that the Russians usually do with a tongue. You might end up with your tongue stuck there. And do not spill it on the floor. The tiles crack and are damaged by liquid nitrogen because of the low temperature. Here's what can happen to you, a little picture. If you spill liquid nitrogen on your finger, frostbite, you flush the affected area with lukewarm water and seek medical attention. And if there is a blister, do not break the blister, just put a gauze on it and go to the hospital. And a little note in case of anoxia. Anoxia is when you breathe, when you are in a closed space, for example, an elevator, and you, first of all, when you move liquid nitrogen in an elevator, put in the liquid nitrogen, press the button to go up and get out of the elevator, take the stairs, and then pick up the elevator when it gets up in the second floor or in the basement. Do not be in the same elevator with liquid nitrogen. You might have an earthquake, a very great one, and you might be stuck with that liquid nitrogen in the elevator for a long time. So in case liquid nitrogen fills up a room, it removes oxygen, and you could, in principle, have anoxia. There, move as fast as possible to a well-ventilated place and try to breathe. Excuse me, somebody calls me at the wrong time. Glassware. Use with great care, use the proper sizes, check the fits, make sure that you know how to put pours on pipettes. Many accidents happen that way. You pierce your hands, your fingers, and so forth. Use glycerin or water to lubricate. For vacuum, you need special glass, thicker. And I will repeat it again, broken glassware does not go to trash. You have a sharps bin, we will go over it again, put it in there. And that is also true for needles. PPE, here you have a nice guy. Points to notice. First, you wear safety goggles. Some experiments is needed, for some experiment is not. Lab coat, if you don't want to damage your clothes. Gloves, and we'll say a few things about gloves. Not all gloves are created equal. Again, you should wear the proper glove for the proper chemical. Long pants, and this is especially for ladies, not mini skirts at work. If you have a chemical spill and it goes over your legs, it will be a problem. Same thing for shoes. Closed shoes, no flip-flops, no open toes, no high heels, just closed, low-level shoes. Of course, there is a variety of personal protective equipment, long list. We have goggles, we have masks, you have face shields. MSDS tells you what to use, where, and how. Gloves, same thing. Check when you use them that there are no holes, and use appropriate time for appropriate chemical. The MSDS tells you what glove to use and what thickness to use. In some cases, when you use, for example, when you're in a clean room, you will need uniforms. You will need a whole coat of armor there. And some protective equipment, maybe not personal anymore, are there, but you're not recognizing them as such as fire extinguishers, such as eye showers, body showers, hoods, and so forth. First aid kits, you should know where the closest one is, and you should inspect from time to time to see if it has everything that you need before the accident happens. If your finger gets cut, it's too late to check the first aid and find out, there are no gauzes here. Face masks. Each has different filter, and each filter is for a different group of chemicals. And they have a color code and a number, alphanumerical, a letter and or a number. For example, this gray one and B are for inorganic gases and vapors like chlorine, hydrogen sulfide, hydrogen cyanide, and so forth. If it's red, it's for mercury vapor. If it's blue, it's for NO and other nitrogen-related gases. Gloves, same thing. You see a selection of gloves here and the comparison for acetone that is widely used and alcohols. Nitrile is not recommended, these blue gloves, for acetone. Surprise. A good thing for acetone is butyl gloves, and so latex, these white ones. Here is a list. Actually, the next two slides have a list. This is not an exhaustive list. You won't find all chemicals here, but in most cases, all nitrile gloves will do. There are some exceptions. And note that there is a weird unit called mil that is basically 0.112 millimeters, and it notes thickness. So 4 mils are 0.1, roughly, millimeters thick gloves. So if an instruction in MSDS tells you 8 mil, you need to wear 0.2 millimeters. So if a glove is 0.1 millimeter, you want to wear 2 gloves on top of each other. I'll go through these. Fume hoods. An issue in labs. They need to be neat and tidy because they are causes of accidents. Somebody puts a chemical in there. The next guy doesn't know it, doesn't check, puts another incompatible chemical. There is a spill somehow. The second chemical reaches the first, and before you know it, you have a boom, a fire, reaction. You don't know what to do. You haven't read anything. Problem. Or you want to use it. It's not comfortable to keep it down. You put the sash up, and the fume hood is not a fume hood anymore. What it is a pump trying to pump the whole room. There is a reason this window, this sash is there and can go up and down. The idea is that there's a pump that pumps air through the fume hood from the room into the fume hood, so that the gases, the chemicals that are in there, the vapors from the chemicals do not reach you. If you open the sash completely, then the pump does not work very well anymore, and the vapors reach you. So here it is, either you follow the safety and you are a little bit uncomfortable with your hands, or you breathe what the fume hood was supposed to keep you from breathing. your choice. Emergency equipment, Anastasia already showed these things. There are showers and eye washers. Use them safely. One notice about eye washers, when you go around in the labs, use them. Open the eye washers so that the still water that is in there flows a little bit, and sometimes they get clogged. By the way, do not dispose of anything. These are not sinks. You don't put your leftovers from water bottle or your lemonade and other stuff there. Back in the day when smoking was allowed, people have used it as ashtrays, which is a big no-no. Waste. Rule number 1, design your experiment. Do not order more quantities than you need. The rest of it will end up as waste. If you need 1 milligram, do not order 5 kilos. To say, I'll probably need it someday. That day may pass, and we'll have to find a way to get rid of it. In designing your experiment, if you want to use a dangerous substance and there is a non-dangerous one, go for the non-dangerous one if it does the same job. For toxic hazardous waste, some have to be neutralized or somehow transformed before being thrown away. And everybody should, of course, read the MSDS and know how to safely dispose a toxic chemical. And most importantly, not in the sink. So here are a few examples. Aldehydes, you oxidize with permanganate. Acids and bases, you neutralize them. You can dilute the acid. You have HCl, for example. You can dilute it and then neutralize it and then throw it away. Throw it away in the sink only if, I'll get to that, if it's a small quantity. And a small quantity is not a kilogram of chemical that you don't need anymore. I'll dump it. First, check the MSDS. Can I throw it away? Is it toxic in general? Is it toxic to the environment? If the answers to any of those questions is yes, you don't throw it in the sink. More interruptions. So, again, small quantities. What small quantities means? 100 grams that is written here is probably a lot, but let's keep it as a limit. 100 grams or 100 mLs per discharge. That doesn't mean that you have a ton of chemical and you can dispose it 100 mLs at a time. You see red stuff here, no toxic, no strong acids. The acetone, the number 3, is a little bit of, let's say, it's not a very strict no. If you have very small quantities of acetone, why is it a no? It's a no because it destroys the plumbing if it's plastic. If you have a lot of water and a very small quantity, an ml, 2 mLs of acetone, first you can let it evaporate, but you can put it in the sink as long as you have a 100-fold flow of water. So you put a few mLs and you let the tap go for at least 5 minutes there. And you see the other list, you can read it. Explosives, obviously you don't throw them away. Things that can react with water in the sink, they will react with water eventually. Chemicals that smell bad, that is biological evolution. If something smells bad, it's most likely bad for you. Oils, like pump oil, you don't throw it away in the sink. It's toxic, first of all. It's dangerous from the environment, second, and it might clog the tubing. And obviously, you don't throw away stuff that polymerize, that make gels. Clogging is the essence. And biohazard materials. You don't want to, I don't know, throw coronavirus solutions in the sink. Yep. I see a raised hand. Is that a question?
It was by accident.
Ah, okay.
This report.
Fine. Maybe I should force people to ask questions. Okay, let's see if we can go to the next slide. And now you see instructions on what chemicals are permitted and not permitted. This is a sort of a gray area. So my recommendation is if you suspect something is toxic, is not good, do not throw it in the sink. And use this list with caution and always in accordance to MSDS. I'll skip these. These are lists of safe to throw away chemicals in the sink. Again, less than 10 grams. That's a more correct than 100 grams. I like it better. Or 100 mLs. Ketones. And now, close to the end, what happens to the disposed chemicals? You don't see it most of the time. You have a bottle in the lab that you put, organic and organic. By the way, where do you put them? Each lab should have a policy on what to do with chemicals. Why each lab? Because different labs have different waste, different kinds of waste. Some people have a lot of water-based waste, some have more organic-based waste, and so forth. So you have containers, usually glass containers. Our recommendation is to use these large plastic containers that are provided by the company that handles our waste. And the moment you put the first drop in, you put a label on the container, waste, but you also need to put what kind of stuff you have put in there, because some chemicals are incompatible. So if you dump diluted acid in a container, and then somebody dumps base in the container, you'll have a reaction. So person B should know what is already in there so that there is no reaction. Writing on the paper that is already on the container is not recommended. Just get a piece of carton, hard paper, and stick a piece from A4 paper and write on there. Hang it on the lid or on the container so that you know what is in there. Now, once a year, usually every June, we have a visit from a disposal company that picks up our sharps that have toxic waste on them and our toxic waste. Note that they will not pick heavy metals. So if you're using heavy metals, they won't take them. So all your waste goes into a warehouse where we keep waste in these large containers. You see, right is the Imbb and left the ISL. These two institutes of Forth have the, I should say, 99.9999% of waste generated, of chemical waste generated at Forth, excluding the institute in Patra. So here you see the containers. These white ones are for liquids. The blue ones are for solids. And what can be a solid waste besides powders and so forth? It can be a paper that you use to wipe a toxic chemical. That doesn't go in the trash. That goes into solid waste. It can be a container that had some polymer, for example, that cannot be thrown, it cannot be recycled. If you have a bottle that contained ethanol and it's glass, you can recycle it. But if you have a chemical, a resin, then you don't recycle the container. It always contains leftovers. So you should dump it in the waste. That goes into solid waste. Special mention, this yellow box to the right is for sharps, needles, and broken glass. It's recommended to separate them because in order not to mix metal with glass. But if you can't just put them in the same, and if you don't have this yellow container, it doesn't mean you should throw it in the trash. Use this blue little barrel. What happens to these? Company called Envirochem, which we have a contract with, which we renew every 2 years, picks them up, and then moves them to Germany, where they get incinerated. They get burned. That's why they don't take heavy metals, because if you burn a heavy metal, it remains a heavy metal unless you are in the sun. In the sun, it might be transformed. And you have the certification, blah, blah, blah. This is more information if you need to contact them for any reason, if you have a special thing that needs to go directly to Germany, so that you have the information to do it. Important, if you don't label your waste, they won't be picked up. If we don't know what the container contains, what there is in a container, don't expect us to put it back, and the company won't take it. It will be, we're stuck with it. And the same is true for radioactive waste. No company will handle radioactive waste. The only one that can do it in Greece is Democritus, the Institute of Nuclear Technology and Radiation Protection. This is where the hospital radioactive waste go to as well. It costs €3 per kilo to dump our waste, so try not to make a lot. But that doesn't mean that if you are uncertain about waste, you should dump it in the sink. The money you save by dumping it in the sink will come up as expenses to replace the plumbing and in costs to repair the environment around Forth. Nearly done. List of references and a list of contacts. Vagelis Karkoutsakis, who is the safety officer for Forth, is first, and the rest of us in the list. And thank you for your attention.